Hello dear students, now let us see basic rules of the binary operations. First of all, the OR rules. The first rule is 0 or A is A, that is any logic value, that is A can be 0 or 1. So the result of ORing 0 or 1 is same thing. 1 plus A is 1. So if you OR anything with 1, in any logic value with 1, any logic value means there can be only two logic values, 0 or 1. So if you OR 0 or 1 with 1, the result will be 1. A or A is A. So if you are ORing two same logic values, the result will be same value, that is 0 or 0 is 0 or 1 or 1 is 1. Then A or A bar is 1. So if A is 0, then A bar will be 1 and 0 or 1 will be 1. If A is 1, A bar will be 0, 1 or 0 will be 1. So always A or A bar, if you find this, then you can replace that with 1. So like this, in any logic expression, if you find 0 plus A, you can replace with A. If you find 1 plus A, you can replace with 1. If you find A plus A, you can replace with A. If you find A plus A bar, you can replace it with 1. The AND rules are 0 and A is 0. That is, if you AND anything with 0, it will be 0. That is, A can be either 0 or it can be 1. Irrespective of value of A, the result will be 0. 1 and A is equal to A. So if you AND anything with A, any logic value with 1, then the result will be the same logic value. A and A is A, that is, if you AND same logic values, then the resultant will be the same logic value, whereas A and A bar will always give you 0. The exclusive OR rules are like this. 0 exclusive OR A is A. So if you exclusive OR any value with 0, then it is same value. If you exclusive OR A with 1, then it will be the complement of that particular value. So, and A exclusive OR A, that is, if you are exclusive ORing same values, it will be 0, and if you are if you are exclusive ORing the A and its complement, it will be 1. Now next is the involution rule, and it tells that the double complement of a digital value is the same value, that is 0 bar bar is 0 or 1 bar bar or complement of a complement is the same value. The absorption rule is A or A and B is A. So this is the absorption rule. So if you find anywhere A or A plus B, then that will be A. Actually, here what can you do is that you can replace this a with a and 1, okay, here, and then you can take common a from both the terms, and it will be 1 plus b. So because 1 plus a is 1, so 1 plus b will be also 1, so you are left with only a. So by combining these rules, we can form this absorption rule. Then a and a or b is equal to a. So this is another absorption rule. Then there are laws of Boolean algebra. First one is the commutative law. It is a or b is equal to b or a. So it does not matter whether the values, the logic values, they are uh, shuffled, the result will be same. Again, a and b is same as b and a, so that will not change the resultant value. The associative law says that a or b or c is equal to a or b or c. So if you perform b or c first and then you OR it with a, is same as performing ORing a and with b and then ORing it with c. So that will give you the same result. So it is called the associative law. Then same thing is applicable for the AND operation. That is, AND operation is also associative, like OR operation. So a and b and c is equal to uh, a and b first, and then the resultant is ANDed with c. So that will give you the same result. So that is the associative law. Then there is a distributive law. So it says that a and b or c is equal to a and b or a and c. So this particular law uh, is also available in our uh, algebra also, okay, arithmetic algebra also. Whereas there is another law, a or b and c is equal to a or b and a or c. So this is bit surprising, that is this, because this or such law is not available in the arithmetic algebra, but this is available in the Boolean algebra as a distributive law. That is, uh, a or b and c you can write as a or b and a or c. So that will give you, so if you perform this AND operation first and then OR operation, whatever result you get will be same if you perform these OR operations first and the result you AND with each other. These laws can be verified by putting the values of the variables a, b and c wherever they are used with the possible values zeros and 1. Then there is a De Morgan's theorem. Two De Morgan theorems are there. First De Morgan's theorem states that complement of products is sum of complements. That is, if you take complement of a product, so a and b is a product, so a complement of product is equal to sum of complements. So if you if you sum the individual complements, then both will be same. So again, this can be verified by putting the values of a and b. This particular De Morgan's theorem can be generalized for more than two variables also. Like if you take three variables a and b and c, whole complement, that will be equal to a bar plus b bar plus c bar, like that. So you can have any number of variables, and the De Morgan's theorem will be true for that number of variables. Second De Morgan's theorem states that complement of sum is product of complement. That is, if you have the complement of sum a plus b, so that is, it is actually a or b. So complement of sum is equal to, you can write that as the product of complements. So here the variables, they are a and b, so you can take the complement of individual variable and take a product of it. So if you make the complement individual, then those particular variables uh, are to be ANDed with each other. So this is the second De Morgan's theorem. So wherever in the logic expression, if you come across a or b bar, you can replace that with a bar and b bar, or whenever you come across a and b bar, you can replace it with a bar or b bar. So these were the laws and theorem of Boolean algebra.